Welcome to today's SCA webinar with Shah Kabir speaking on In Search of the Right DCA Method for Unconventional Reservoirs. Before we start today's webinar, we would like to take a poll of the audience. And so I'm going to launch the first polling question. What is your primary discipline? And so we're starting to get the votes in now. It looks like we have quite a few petroleum engineers in the audience. They're running way ahead of the geoscientists. So far, it's about 65% petroleum engineers. And most of you have voted, so I'll go ahead and share the results. We have 68% petroleum engineers, 32% geoscience. And the next polling question is, how many years of experience, a full-time experience, do you have in the upstream oil and gas industry? So we're getting the results in now. Looks like we have a pretty diverse group here today. There's some in every category. So most of you have voted now, so I'll go ahead and share the results. We have the largest group is 35% in the 11 to 20 year experience group, followed closely by 31% in the 1 to 10 year group and 23% at over 30 years. So thanks for everybody for joining. And I'm going to share some slides here. So again, you are logged into today's SCA webinar in search of the right decline curve analysis method for unconventional reservoirs with Shah Kabir. Shah is in the process of retiring again from teaching petroleum engineering at the University of Texas. I think he's still working on several projects there. He is also a full-time consultant with CS Kabir Consulting. His industry experience includes 40 years with a multitude of different employers, including Hess, Chevron, Schlumberger, Arco, and Dome. And he has taught in a number of different in-house corporate courses, including courses for SPE. He's done guest lectures at Stanford, Texas A&M, USC, and of course U of H. His expertise includes transient pressure and rate testing, wellbore fluid and heat flow modeling, multiple aspects of reservoir engineering. Shah is very well published. He's published over 100 technical papers and has served in the editorial board of 3 journals, the books committee for SPE, and is currently authoring a book. He has received the highest award that SPE offers, the honorary membership of SPE. And he also received the SP Reservoir Description and Dynamics Award back in 2010. So the class that Shah teaches for SCA is entitled Reservoir Management of Unconventional Reservoirs from Inception to Maturity. It's offered next month, August 16th through 17th in Houston and SCA's Training Center. So be sure and contact us if you're interested in attending this in-person course. You can also contact SCA's training department if you would like to have this course brought to your office, or if you would like to discuss other classes that we offer. This is part of our regular webinar series that we have been offering for several years now. Coming up on the calendar, we have John Rodson speaking on August 18th on deep water sedimentation. And then looking ahead to September, Dr. Christine Illig-Economides will be speaking on the topic of carbon capture. We've been offering a number of live online classes since the pandemic, and so we have several that are scheduled to be held in the near future. Nathan Meehan is speaking on energy transition for petroleum professionals. Lee Richards is teaching on drilling fluids. And Larry Lake and Jerry Jensen are discussing managing mature oil fields with capacitance resistance modeling. And John Lee is speaking on production forecasting for low permeability reservoirs. And then finally, we have Leo Redhart and Garrett Nitters on well stimulation workshop practice and applied. So look to SCA for all your training needs and also for consulting, direct hire services, projects, studies, and training. And so I'm going to pass the presentation rights to Shaw and let you take it from here. Okay, we see your screen.
Okay, you can hear me too, right?
Yes.
Cool. Hello, everybody. Good afternoon, and welcome to this webinar. I hope it is useful and interesting. I have been studying unconventional systems for a little over a decade, so I'll share how I started my journey to where I'm at. Okay, so here you go. Okay. So this title is a little bit interesting in that I don't know the answer to this question. So what's the best one? And so I'll give you a larger perspective, and I can give you some of my personal opinions. The reason for that is frankly speaking, I have not studied all of the methods that have, let's say, come out the last 3-4 years. I've read them, but I have not used them all. So here we go. So so there are 2 sets of tools in this domain. The DCA stands for decline curve analysis, which we need for our reserves estimation, and we have to file, every operator has to file for their annual reserves report to ACC. So we need that. So here I've listed some of them. Bear with me. I have the pointer option, laser pointer. Okay. So here are some of them. And so what I'll do now is show you some of the others. And I'm familiar with most of them, but not all of them. So the reason that these 2 items are, they both came from Texas A&M, coincidentally, they're similar, and they stay on the conservative side. So that's something that that's one of the reasons for my preference for these 2. So when you say modification of Arps, because Arps method was intended for conventional reservoir system, but when in unconventional, it's a little bit different ballgame. So the question is, when that modification is made of the conventional Arps, it is done with knowledge, of course, but it's not that stable or reliable in that sense. When we have to switch from one flow regime to the other, and there are better tools. And lately there have been the machine learning. That's what ML stands for. People have offered modification of Arps method to account for that, and I will briefly introduce you to Gupta et al. methodology. Moving on, then there are analytical tools. I think all of you recognize the analytical methods are more reliable. Why? Because that methodology is anchored in physics. And so I was involved in one of those studies not too long ago in UT Austin with Professor Larry Lake, and that's his student who is now at Chevron. So we'll talk about that and its efficacy and all that. And this is also from UT, recently came out. And one of the students, master's student, Pan, did that with the CRM, capacity resistance model, which we use regularly for water flood or CO2 flood, whatever. So that can be all done. So these things keep coming. So there is no shortage of them. The question then is, which one do you use? You've got so many. So that's what I'm trying to answer. So this was our first attempt, for my first attempt to learn what is going on. So back in the day at HES. So the main question we had, I asked myself is, okay, all the tools that were out there back then, they pertain to gas reservoirs. So the question I had is, okay, how do they still work for oil reservoirs? Because they are not the same, they're similar, but not the same beast, in that the permeability is a nanodarcy for gas as opposed to microdarcy for oil. So that was the question I had for myself. Okay, so we'll use the synthetic as well as to understand what the we want to share with you is that, okay, if we use simulator generated data, and can we interpret that? How do you do that? And of course, the field data. And then we want to estimate the oil in place and within the stimulated reservoir volume. That's what SRV stands for. And this is the context is the tight oil is the context is the Bakken play. Okay, and then we'll compare our solutions with the power law exponential and stress exponential as well as CRM. There may be. Okay. So what we did is said, okay, so we have a horizontal well, and these are the transverse fractures that we created at different stages. And so how does it play out? The streamlines play out. So in day two, it's the flow is occurring and feeding into the fracture. And then at late times, it's we're seeing the particular domain. So back in the day, we didn't have the concept of discrete natural fracture network or DFN. How do we put them in and all that? We didn't have numerical modeling capability. These days, yeah, we do. Anyway, we are trying to understand. So when we say the stimulated reservoir volume, that means that we are talking about this boundary. So so it's not the same as the reservoir boundary in a conventional reservoir system. So that's a big difference. So in simple terms, we're dealing with much smaller pore volume. So how do we know what's going on in the system? Okay, to that end, if we use this sort of diagnostic plot as we do in conventional red transient analysis, we can gain a lot of insights, what's going on. So what we do is that at the early time, we see the half slope line. So that's a reflection of how the fluid is flowing into the fracture, into one stage of the fracture. So that will create the half slope line. And later on, when we see the total span here, so that will give us the unit slope response or pseudo unit slope response. And that will give us the so-called the drainage volume of the stimulated domain. So that's a metric that we can use for to gauge, okay, how successful was the stimulation job in a well A as opposed to B or C. So this is again, we have synthetic data. So everything is fitting nicely. That's the cumulative production, and that's the decline they're seeing. And we are predicting for 40 years. Why 40 years? That was the company directive at that time. So that's why we may have a 1-year data, but we have to extrapolate to 40 years. That was not very wise, but that was the day. So here you go. So as you can see, that the power law exponential would give you conservative than the Arps, even though this was modified. And then we use the stressed exponential model. And so it's a 2-step process. So it's the recovery potential, and it has the complete and incomplete gamma function that is used. Everything can be done in Excel. So that's what we did. I said, okay, we pretended that we have this data and the whole data set, but we said, okay, this is known. And we pretended we didn't know, and we wanted to extrapolate and just to check how good the fit is. So when we did that, we got 857, and the simulator result was 854. So we thought, okay, this is good. It's working out very well. And then we said, okay, how about looking into the similar data through the lenses of other diagnostic tools. So for example, here, what we are saying is that what if we have the number of fractures in an idealistic model? So this would the case would be for one stage of fracture, 15, and so on. So what was interesting is that for this particular well, we had only 10 fracture stages because these were the early stages of field development. And it fitted with the 40 stage of fracture. So it was a head scratcher, what is going on? Well, as it turned out, so here's the well, and here's the seismic map. So this is telling us that, okay, we have, the only thing I know about seismic is that the bright colors are good. So as you can see, about 1/3 or so domain of the fractures that we created experiences stimulated reservoir volume by way of presence of natural fracture network. And this is also observed with another tool, which is that Colorado School of Mines, the transient PI approach. sorry, we don't have time to get into details. So what they were showing, the authors were showing, is that, okay, if this domain, when it becomes horizontal, and this is a trial and error solution, then we know that we have seen the stimulated reservoir volume, and it is trying to, and if this is contained within one or so log scale, then it signifies that we have natural fracture system, which is corroborated by the seismic response in this case. So this number that we are getting, we get the in-place volume, agrees with, generally speaking, with what we are estimating with other methods. So on the other hand, if we couldn't create a transverse fracture, say if it is a longitudinal fracture, this is what happened for one of the real wells. Depending on how the wells were drilled, then it will not exhibit that. So it is trying to tell us that, hey, we couldn't create a transverse fracture. Okay, so going back to our well of interest, we can do, given that we had the measurements of pressure at surface, which was, we were able to convert it to downhole because we had single phase oil production. And so we can get a good match of cumulative production, and so is the rate. And we're able to also history match the pressure, and that's the diagnostic plot. So here toward the end, we are probably seeing some footprints of the inner slope response, but most of the time it is not. It is showing different type of responses, and we'll see whether we can come to that. But here, what we are seeing that we are able to, the model that we picked, we're able to history match all three responses. We have the rate, cumulative production, as well as pressure. So that gives us a lot of confidence in what we are doing. Okay. And then we can do the Arps. Arps, as you can see, it's much higher than the power law exponential. Now, but the reality is that the pressure measurement in, especially in oil field situation, is an exception rather than the rule. Why is that? Because we put in artificial lift. Sucker rod pump is most common. So whereas you can convert the wellhead pressure to bottom hole for gas or gas condensate system, but for oil reservoirs, that is an obstacle. So what I did is said, okay, how about assuming a constant bottom hole pressure? I don't know what it is. I assumed a number. Why? Because I want to generate, this is my rate profile. So this was, the fracture was re-stimulated. And this is a re-stimulation. And then this is when they installed the artificial lift. So when we did that, so we are not trying to use that as a quantitative tool, but we are trying to figure out, okay, do we see the inner slope response? So the inner slope response allows us to estimate the in-place volume. So that was the motivation for doing that. And then said, okay, yeah, you can do that. It's a good assumption because the assumption of a constant bottom hole pressure is a good one if you're putting an artificial lift such as sucker rod pump. Okay, we can do the parallel exponential and also Arps. As you can see, Arps will always give you optimistic solution. So hence my preference for either power law or similar tools, and or stretch exponential. It'll give you very similar solution, whereas conventional Arps will give you very optimistic. And so the other thing that we can do, because our management was seeking 40-year projection, then we're saying, so look, don't ask for 40 years because we know the answer in months, because for all practical purposes it becomes stable. You cannot see there is a minute change, but we drew a horizontal line to indicate that. Okay, so this is the piece of work we did, and we said, okay, how about can we bring in the concept that we have to learn with the capacitor resistance model? So we said, so the way it works is that this is our stimulated reservoir volume, SRV. We have a long horizontal well with the transverse fracture. We call it block M. And then the question was, how many of these do we need to represent the different blocks? So this is more for conceptual understanding of the system rather than for absolute truth. So what we learn is that, okay, as time progresses, we will see the decline. Okay, will decline in block M and block 3, but for block 2 and it'll be different. In other words, conceptually, what we are saying that these the outer blocks, they have to feed the inner blocks, otherwise the system will quit, right? So this is for more of an understanding of the system, how it behaves. So as time progresses, so in simple English, what we can say is that if the outer blocks don't communicate, so imagine that the block 1, 2, etc., they are not communicating with the inner blocks. So in other words, if these folks are not contributing, then this will drop dead in a hurry. And there are quite a few cases that we encountered in the real bucking play. But people don't talk about them. But that was part of the motivation way we investigated this. So how did it work? We said, okay, we history matched part of it, and then the forecasted, and the solution was, wow, okay, it is working. And then, so sorry, the line went missing. So we history matched just part of it. We got the parameters and we forecasted the rest of it. And Marcellus, wow, so CRM and actual production match was, so our history match was this part. We see the dark color, and the rest were projections. So, and the stretch exponent. So the point is, so we are initially very excited, but then the CRM, what we found out that doesn't have the back in the day, but right now they have Professor Legg has found a solution. So it would not be a good tool for future predictions. It's a good thing. It was back in the day. And if you're doing it over a short time period, relatively speaking, it was all right. But if you have to go much longer period of time, then it was not good enough. Okay, so we tried various cases and it worked out. We are very excited. Okay, so one of the issues that we encounter in unconventional play is the number of wells we have to sheer number of wells we have to drill deal with. We have to deal with hundreds of wells, literally. So do we have? So you need an army, so to speak, to do all that work. So can we group the wells? And so instead of working with, let's say, 100 wells, can I work with maybe 3 or 4 wells? And by way of well grouping. So let's see how it goes. So before we get into that, just to give you a perspective. So this is a cumulative production. So if we have Arps exponential, so that means we have a boundary dominant flow, then it will have a closure in relationship. See, the cumulative production becomes flat. So that's the stretch exponential model parameter. And Arps, the reason we should not be using Arps for unconventional, that when B is slightly greater than 1, then it becomes there is another closure here. So it will take you to the moon when you extrapolate this curve, so to speak. Whereas if you have stretched exponential, you have a closure in relationship. So that's the point we're trying to make. So in this particular, we're going to talk about stretched exponential. And then this thing came up, and again in concert with the model. And so the model is that if you have a microseismic data, and you don't need that, but you can work with this. And so the analytical model was derived. This piece of work was done at UT Austin. And then it can come up with the simple analytical expression, which you can do in Excel. So what we're doing, we call it series model, is because we are saying that in the matrix, we have flow that is feeding the, this is the stimulated reservoir volume that I was showing you earlier. So this is the matrix, the blue. So it's feeding this network, and whereas this is the flow with inside the fracture system. So that's what the matrix and fracture is all about. So why should we be interested in that? It's a independent of fracture geometry and orientation and kind of thing. Yeah, you can do it in Excel, and it has theoretical foundation. So we validated the solution many different ways, and so in series model, so we have the matrix, and then that's the fracture. So what we come up with in the real world is that you have the oil rate or gas rate, doesn't matter, and you see a point of inflection, okay, that corresponds to the so-called fracture boundary effect, and then the matrix transient flow, and then the it reaches out to the larger boundary. So in other words, if we didn't have a natural fracture network, so you can move this thing to here. So your total outcome would be this. just by moving this guy to the left. So what I'm trying to say is the presence of natural fracture network is a must in the system to be able to get meaningful reserves out of a given well. So here is a real field data from Bakken play. So this is the, I'll not spend too much time on the early time data. So here we get is a unit slope response, and this is when this is the pressure response. This is the flat response, reflects the installation of Chakarot pump about 100 days into production. And we see that production profile match. And you see that point of inflection. So the green is your data, and then you see the point of inflection, and then so we can project this is the outcome. So if we didn't have this kind of response, then it should be moved to the left, and the well would be all but gone. So similar thing for another example. So as you can see, the half slope response followed by unit slope. So unit slope implies the boundary dominant flow, whereas the half slope implies the linear flow in the early times. Again, artificial lift was implemented at that point. Again, we get a point of inflection and all that. So let me briefly talk about some of the other tools that are in play. Done by studies, other studies. As you can see, all kinds of models, exponential, that will give you the absolute minimum outcome. That's something we know. So this is the modifier stretch exponential. So this is better than that. And this is the power law exponential. So stretch exponential, power law exponential, they give you very similar outcome. But the other models like Duong, for instance, it is because it's rooted in linear flow modeling approach, it'll be always on the optimistic side of the equation. So even after a modification of hyperbolic trend, it will give you a higher outcome. So Duong and any Arps type of approach will give you a higher outcome. And this is consistent. This trend is consistent in all the plays, whether it's gas or oil or gas condensate, what have you. But the good news is as time progresses, they all tend to converge depending on where you are. Whereas Barnett and Bakken are in good shape, but in Eagle Ford there is a big uncertainty. But then you have to look at the y-axis. So this is another SP article that shows the efficacy of different models or correlations, and based on whether you're talking about ACC guidelines and all that. So we have the traffic light. So if you use the power law exponential or the stretched exponential, then you are in pretty good shape. Okay, you have a lot of green lights, and you are meeting the ACC guideline as well. And so this is just to give you a 10,000 feet overview of some of these items. Let's carry on. And so the backcasting is that, okay, you can hide some years of production. and you presume that this is all you know, and you do the forecasting, and then you reveal to check out how well it's working or not working for you. So this study pursued many wells, as you can tell, in multiple basins. And here's one example. So as you can see that for some reason, Arps was on the pessimistic side here. The Duong is there. And that's the data. Okay, let's see. Okay, so for, as you can see, in this particular case, Duong is giving you a very optimistic solution. And they had used another method, rate inverse. That's very optimistic. And in this case, this is some form of modified Arps they had used, and that's on the pessimistic side. Okay, so let's go back to well grouping. So how do you do that? So ideally, what we said that the way we can do the well grouping is that use the productivity index, rate over delta P, initial pressure, and this is the flowing bottom pressure, which is changing at every time step. So we said, okay, because we in unconventional play, we don't have this PWF in most scenarios. So we said, okay, let's go along with the rate. That's all, because everybody has opened their valves all the way, so to speak. So when we do that, and let's say these are based on real data, and I said, okay, we have this set of distribution. And then the question is, how do we group them? And then we said, so for this example, because we are testing our own thoughts at that time, we said, okay, we'll have 4 groups. And we have, now the question then you may ask, okay, does this well belong here? Or should we not move it to this? Yeah, but we are just testing our hypothesis, how well it works. So we had a quote unquote aggressive approach. Okay, the Barnett Shell play 500 wells. We said, okay, this is good. So we converted all the 500 wells into 4 wells, 4 pseudo wells. And we are testing in one particular case, and we found that the solid portion of this circles that we fed the model with this data, everything to the left, and we projected. We said, oh, this is the P50 outcome. It's working out quite well. Okay, so this is how we did our things. We said, okay, the outcome would be here. That's the P50, the red triangle, and this is the range of solution, P10 to P90. Okay, so in most cases they are intersecting. Here's one case. This is off. Here's another case. It's very low. But remember, we had very conservative number. So here the Marcellus, a similar approach. We took 224 wells. And Elm Coulee, it's a tight well, it's a Bakken play. So we did that. This is just to test how well this is working or not working for us. So here's the summary. So we found that for the most part, for all these wells, that we can say that 75% of the time it fell within that domain. And the percentage of wells that are above P10 and below P90 are about 10–15%. So couldn't we have done a better job? Of course. But we did it purposely to teach our own curiosity. So that was the motivation for pursuing it. So instead of 4 wells, if we just rearrange some of them or create another 1 or 2 pseudo wells, the outcome would have been over 90%. But we did it to learn few lessons. Okay, so here's another example for a comparison. So we have 52 Burnett wells. Here we history match this data set, and then we forecasted the performance. You see that this is the real data, and the pink is the stretched exponential model. And Arps and Duong, the yellow and the green, are going to be optimistic. So we have learned those things in many different ways, and this is just another example. So this is a recent outcome. We are not, I was not involved in this. So what we found that, okay, we in Arps modeling, we assume the decline rate D is constant for conventional, which is true. But in unconventional play, D is variable. So they have a methodology that can handle this, the variable D. So you might say, well, you have a mess. So how are you fitting this? I'll skip the details for now, but overall, this is how it's working out. So they fitted this, and then this is the rest of the data. So this is a genuine data-related issue. We do not know the details, but that's the overall match. So this is the overall finding that they reported. So for Hainesville, this is their approach, VDMA, variable D factor, and so they are getting everything almost zero error. And whereas power law and stretch exponential are giving on the pessimistic side, not by much, less than 5% here, and stretch exponential here is maybe a 1%. So, whereas Arps, Fetkovich, Duong, and all that, there will be double-digit errors. So in that context, let me point out that we are investigating a lot of items and we're writing a book chapter and so on. So data quality is a big item of interest. Then the frac hits, the interaction when you are drilling an infill well, the parent well would interact with the child. And then anomalous diffusion that comes into play, not only in unconventional, but also in conventional systems. And then when you are doing any CO2 huff and puff type of operation, we need to know what's going on. So we cannot just fit decline curve through everything. We need to understand the underlying physics. So let me summarize the outcome, the lessons that we have learned so far. We had both the power law exponential and stretch exponential. They are good options, and because you are staying on the conservative side. That's the motivation. And the analytical model front, we see the series model and the PAN CRM are good because they have theoretical foundation. And the beauty of well grouping, because we have to handle a large number of wells, is that it can handle any model or correlation that you like. It's just that instead of doing it hundreds of wells, one at a time, you can minimize that burden. That's all I had. Thank you for your attention.
Thank you very much, Shah. And I want to remind our listeners today that you are muted. So if you would like to ask questions, now's your chance. Just use the question feature in GoToWebinar. Type your questions there and we'll capture them and read them back to Shah. So Shah, you mentioned on slide 44 that there were a number of items that you didn't really have time to cover today. That you could elaborate on, and perhaps you could talk a little bit more about those topics.
Yeah, maybe I can share.
Yes, you still have the presentation rights.
Okay, so can you see my?
Yes, we can see your document.
Okay. So one item I'd like to point out is the so-called frac hits, because what we're doing in the industry these days is that we have a parent well, that means older well, and then we bring in a child. They're naughty, as we all know. The point is then there is an interaction that occurs. So that interaction is harmful to the parent. Okay, so what they are saying that, okay, you can do this, but don't do this. So don't go side by side. Then there will be a serious interaction. Or if you want to go parallel, then you just offset it. I think this is a bit tricky, but conceptually, if you do it, because what we don't know is the presence of natural fracture network, and through which the interaction can occur. So we don't have to physically contact, but what we are saying, okay, I'm trying to activate my, anyway. So that's one hot topic, because most operators have gone in and tried to enhance the recovery, but in so doing, the experience hasn't been that great. That's my take. The other item is, very quickly speaking, is that anomalous diffusion. So what we have here is that, so here's my well, and we created these transverse fractures, and then, as we all know, that we have presence of discrete fracture network in the system, DFN, is to go by. So what happens is that this, to what extent they are communicating with the induced fractures matter. That provides the difference between the well A versus B in a given play. So what we don't know is the intensity of this discrete fracture network in a given system. So what that means in simple terms is that if you have the diagnostic plot on the log-log scale, that will give you slope of, if I can expand that just a sec. Yeah, so the slope is the only thing that we are familiar with in the industry is it 0.5 or 1. So as you can see, it's neither half or 1. So this is called anomalous diffusion, and that's what triggers this sort of outcome. And I'd like to draw attention to this, which we had seen in the context of the series model, that it comes down and there's a point of inflection. So this would also occur, but this is not curving downward yet. So it will, had the model run gone longer, then it would be curving downward from that point forward. So this is how things play out in this particular domain, that when you have, yeah.
So we've received some questions from the audience.
Okay.
One question, is there any cutoff for permeability where Arps stops working, either in oil or in gas?
Good question. It all depends on the setting, but for example, I've worked with the low permeability, single-digit permeability in North Sea, in water flood and so forth. Yeah, Arps would work even for single digit millidarcy permeability, but if you start to go lower than that, then we have to take a closer look what's going on.
Okay.
I would say, yeah, even 0.1 millidarcy range could be okay, but beyond that, it would be tricky.
Right. Next question, is there any similar work done in the Powder River Basin in the Niagara or the Turner formations?
Yeah, to my knowledge, similar work, similar to which?
I guess similar to comparing all the various decline curve analysis methods.
Oh, okay. It rings a bell, but I cannot point my finger at it from the top of my head. But I can dig up something and probably forward it to the concern. Yeah.
Great. Next question, can you comment on the effect that free gas flow on the reliability of single phase gas decline curve analysis methods?
Free gas flow?
Free gas flow, single phase. And so how does that work with decline curve analysis methods? Which are the most reliable if you have free gas flow, single phase?
Yeah, so a lot of this Burnett shell, that's what it is. That's gas flow and single phase, and yeah. So it works.
So would you recommend the power log? Which of the decline curve methods would you recommend? For
yeah, power law or stretched exponential. Yeah.
Okay. And then here's kind of an all-encompassing question. Which method is considered best as of today? So they want you to answer the title of your webinar. Which should we use?
We can flip a coin, either power law or stretched exponential. On the as far as the let's say
Well, I guess you said the VDMA method had a 0% error, so that was maybe less error prone.
Yeah, the only reason for my hesitancy is that I have not played with it myself. I'm not doubting what the authors have done.
Okay. Something to look into.
Yeah, so it's in terms of the correlations, yeah, stretched exponential or power law, but in terms of model, you can use the series model or pan CRM.
Right, and I guess the power log was the one you said hit most of the green lights for the SEC chart, so that's
Right, I
definitely in
think,
favor.
yeah,
And the CRM method is something that we actually have a class that Jerry Jensen and Larry Lake are teaching for SCA. So lots to explore. So that's all the questions we have from our audience today. So I'd like to remind our audience that after today's webinar ends, you'll receive a link to a recording that you can share with your colleagues. We'll ask for your evaluation of the webinar, and we'll give you more information about how to register for the class that Shakabir is teaching in August, Reservoir Management of Unconventional Resources from Inception to Maturity, of unconventional resources from inception to maturity. And that's in Houston in August. And so I'd like to thank all of you for attending today, and we look forward to seeing you at future webinars. Goodbye.